All right. So yeah, hey everybody. I'd love to introduce you to Licheng Liu from University of Minnesota. He's been doing a lot of interesting work in understanding global ecosystems via the lens of machine learning and using this new toolkit to, well, give us new insights. Yeah. Welcome, Licheng.
Okay. Thank you so much. I'm really glad to be in this group and introducing our exciting findings and using knowledge-guided machine learning model to advance the ecosystem understanding. And it's going to be, I prepared about 40 slides, but I tried to go through them all of like within 40 minutes, and I will leave 20 or 15 minutes to Q&A. But if you have some urgent questions, but feel free to interrupt me. Okay, seems like slides goes well. And the outline is very simple. And I'm going to introducing something related to the ecosystem and what is ecosystem and ecosystem modeling and how is applying knowledge-guided machine learning with some real-world examples in agro-ecosystem and natural ecosystem. And first of all, so why I'm interested in the ecosystem, because over millions of the year evolving the ecosystem, sustain life, human well-being, and the planet. It's our surroundings. But along with the global population increasing, we have met some problems in the ecosystem. We have found the land use keep increasing, the water use keep increasing, and energy, we require more and more energy. And the subsequences like we don't want them, like tropical forests are starting to lose, and the nitrogen to the ocean will cause some dead zones, and also carbon dioxide may cause the global warming. And to sustain our human being, we need to sustain the ecosystem. In order to do that, we need to understand the carbon, nutrient, and water cycles in the ecosystems. They are highly related to our crop productions, our drinking systems, and also the back end supporting our carbon and the water. In order to understand them, we need to understand that these systems are not individually existing. They independent with each other, and also they are influenced by the climate systems significantly. Like we need, in order to better understand these cycles, we also need to consider the severe, some extremes, extreme climate events like increase the frequency of the rainfall, increased temperature, very much to happen in the future. And also the systems human can also manage through the fertilization, irrigation, some emission reduction strategies, and also land use planning, conservation practices, and restoration. But in order to manage the ecosystem, we need to measure the system, because we can manage if we can measure. The thing is, measuring the ecosystem is particularly challenging because of the nature of the ecosystem and the high heterogeneity and the very complex the processes behind that, with incomplete understanding of the physical biochemical laws and its parameters. It's quite different from the other systems, like we might already very much known the physics controlling, like climate system. We have fully understand that of the representations and the parameterizations in most of the cases. And let me go a little bit details of these two challenges. The challenge one will be the ecosystem high heterogeneity. And here is an example that we only have one observation tower at Conversely tower over a large land. But this tower, you can see this poor tower cannot cover the whole scenarios. It can only give you one integral over a large space. That is a sparsity of the observation issues or heterogeneity issues. Another thing is the underlying processes. Here I presented the processes controlling the methane cycles, and you can see it has influxes outfluxes and also some underneath soil processes, plant processes, and related to the water as well. So the ecosystem, those physical and biochemical processes controlling those the ecosystem on the ecosystem outcomes are very complicated. If we want to have a better understanding of the ecosystem, we need to have a better measure of those processes, but which is very hard. And then I would like to give a breath here, and the AI revolution is here. Not everything is hopeless. We have seen something very good advances, like the large language model already enables human-like conversations, and those Nobel Prizes awarded for the application in AI of AI in physics and chemistry, and also the deep learning powers most of the AI applications in our life days. And we are start to think, how can AI be used to improve the ecosystem understanding? So that is my interest comes from, and I'm very interested in using AI and multimodal data to advance ecosystem understanding, and by incorporating the ecological knowledge into the AI for ecosystem. And the data include like the in situ and sensor networks, those remote sensing data, meteorology data, and biochemical observations in the lab, and also some geospatial survey data can also be used, and the synthetic data being simulated from those models. And on the right hand will be our my interest in some ecosystem problems like greenhouse gases, carbon sequestration, productions, which are areas I'm heavily working on. And water quality, quantity, air quality are something I'm interested and have some projects going on, but not being going to be presented in this presentation. And later on, some soil health, biodiversity, natural hazard. And I believe I have seen some really good applications with AI. And I also have the belief that incorporating the ecological knowledge into the AI can better help them. But I didn't explore by myself. So the outline, the second part, come to the second part, I would like to go a little bit details. What is a knowledge-guided machine learning, and what is ecosystem modeling? And first of all, let me introduce in the modeling. And modeling is, in this group, should be very familiar, that it is a way we measure or predict phenomena that are difficult or impossible to measure directly. And here is two-dimension coordinates. I would like to introduce the different kinds of models and compare with them. The x-axis represent the use of the data, and while the y-axis represent the use of the scientific knowledge. Unfortunately, the field measurements, or the normal way we measure the conventional way we measure the environment, are on the lower corner, lower left corner of these coordinates, because only single point of the data collection can provide limited data and limited scientific knowledge. And on the high end of the use of scientific knowledge, I would like to introduce in the process-based model. And a process-based model is generally is a numerical representation of one or several processes characterizing the function of a complex systems, mainly based on the established scientific understanding. And the right side and right end is one of the just one illustration of a process in the process-based model, demonstrating the substrate concentration changes like the ammonium nitrate concentration in the soil, those changes, and the oxidation production rate, how it calculated. And a full set process-based model can have dozens of such processes with hundreds of parameters and over 1 million lines of code. So that is something you can imagine. I have summarized the pros and cons of the process-based model. Even though the process-based model is a glass model, it has high interpretability and normally needs low data to calibrate. The accuracy, efficiency, and the structured data flexibility are relatively low. And especially in the high heterogeneity situation, which requires high resolution and the multi-scenario simulations, such efficiency and the ability to welcome in new data limited the process-based model to be extrapolated everywhere.
So, question on
Yeah.
this point. So, this is, I mean, this is a standard debate in many communities.
Yeah.
So now, the benefit of such process-based models is they act, they constrain you to act in this particular way. The limitation is that, well, that's all they can do.
Yeah.
So now, I guess in this field, to what extent, what are the dynamics that these process-based models miss or are over-constrained for?
Yeah, this process-based model, basically, they are in ecosystem modeling. They are also in a broad spectral. Some of them are simplified by some processes, mainly driven by some empirical relations derived from some lab data and small amount of field data. And another group of model, and they are developed mainly trying to incorporate in only first principles describing the ecosystems. And both of these models have their own specific limitations. And the using empirical like those empirical relationships in the model, they are limited by the very good explanations of the detailed processes and not very generalizable to the broad scale. And another side, like if you develop your model using all the first order principles, the first thing would the first limitation would be we have not sufficient understanding of the process-based models. The structure uncertainties is high, and on the ones so the complexity and with the complexity increasing, the model should become more and more reliable. But the reality is the flexibility and the accuracy is keep decreasing, and it becomes a overfitting issue to some previous derived scientific knowledge or previous data, and that is a problem. And and I don't think this problem can be solved in the recent like in a short period of time. It's a long-term plan, and the long-term solution would be the keep developing this process-based model until every piece of the understanding is complete. But that will be our ultimate goal, and that's why I summarize the process-based model is not a perfect process-based model. It's a current maybe state of art process-based model. They are facing such problems, and but I still think the process-based model is the scientific foundations of should be the scientific foundation for many current models and many current AI models, and so that I don't think they are like less useful in the era of AI. Like, but they should be very useful. They should be even more useful than before because they can be the guide for the AI. That is something I would like to introduce. How the process-based model, we can leverage the process-based model, reduce the complexity of some models, or increasing the complexity of some representations to in the AI models to make the efficiency and the flexibility increase, and while the accuracy increase. So that is something I'd like to say. But thank you for asking that question.
That makes a lot of sense. Thank you.
Yeah. We can have a deeper discussion later. But let me introduce another side, AI models. Most of the groups, people here should already very familiar with machine learning models and its applications in different kinds of fields. And that is, I use a conventional black box machine learning models. and it's at a right end of the use of data, but lower end of the use of scientific knowledge. And the machine learning model is built on the machine learning algorithm trained primarily based on the data to recognize the certain patterns and make predictions. And here, right side is some examples of the machine learning architectures. However, most of them are black boxes and used as a black boxes in many applications, even in the large language models. We believe they have really good advances. I have already summarized in the below table. They have a really high accuracy. They have really high efficiency and structured data flexibility, but we are hard to interpret the results. And sometimes, and in most of the cases, this model are hard to, will need a huge amount of data to train. So that might be the limitations of the conventional black box machine learning models, especially in the scenario ecosystem modeling. We need very good explanations and to explain those results. So the black box machine learning may not be very favored. So can we combine the two models to overcome the shortcomings in the ecosystem modeling? The answer is yes. Here are some, there are already some very good applications in many different domains. In the ecosystem is like started maybe from the 6 years ago, and a group of people, the group people using hybrid AI models in ecosystem modeling is growing and making very good progresses. And here, hybrid AI models can overcome the previous discussed limitations. Some examples like the knowledge guided machine learning model, which I'm going to introduce in the later phase, and the physical informed neural network, biochemical informed neural networks done by H.E. Law from the Cornell, and also differentiable programming, also very useful. And they can overcome the two challenges I have mentioned before, the high heterogeneity issue and the lack of the sufficient scientific representations in representing the soil plant processes. The hybrid AI models aims to combine the data efficiency with the mechanistic realism. And here is I kind of think this analogy is a little bit easy in this group, but I still would like to introduce in this way. The analogy that I always using this analogy to explain what is knowledge guided machine learning. And imagine the black box machine learning model is a robot. If we let the black box machine learning model learn a task like cooking a pasta, it will try millions of times of different combinations of those ingredients and different observations until finally get your edible pasta. And what we can do to reduce the efforts is we already know some good recipe, and we can encode this recipe into the robot brain before the testing with the real ingredients we call knowledge guided architecture. And we also have some very brilliant chef can cooking very delicious pasta, so that we can let the robot to observe the chef. We call that knowledge guided pre-training. And later on, during the training trajectory, we can also set up some rules to let the robot didn't violate some very fundamental rules, like the do not burn the food, the mass will always balance, and the energy will not disappear or appear with no reason, so that the robot will learn faster than ever. With those three main categories of the knowledge guided strategies, I'm going to introduce in the real applications in the agri ecosystem and natural ecosystem with examples. Okay, the example one will be in the agri ecosystem understanding with KGML. And here I'm going to introduce in a small subcases in nutrient and carbon. And mainly they are focusing on the U.S. Corn Belt region, mainly famous for the really high corn production in this region. And the thing is, if you want to plant corn and get a really high grain yield after a year, you need during the corn year, you need to fertilize the soil. And the fertilization will cause subsequent greenhouse gas emission, nitrous oxide, which is powerful greenhouse gases, more powerful than the over 200 more powerful than the CO2 as a greenhouse gas, and is induced primarily by the fertilizer. And over applying the fertilizer can also cause water and air pollution and the land degradation. So that's why we care about the fertilization over the cornfield. And also this assimilating the N2O emissions are challenging because the dynamics over space and time are controlled by a large range of biotic and abiotic factors, and so that it has hot moments and hotspots, and meaning sudden peaks or the red dots. So how can we use AI models to do a better N2O simulation? And here we kind of publish our first paper based on trying to understand the agriculture natural oxide flux. And in this paper, we are trying to improve the agricultural N2O quantification, especially trying to capture the N2O hot moment. And how did we exactly incorporate the knowledge in this AI model? And the first, we very simple, we open the black boxes using a hierarchical structure and two-layer structure to simulate some intermediate variables first, like the soil water, soil oxygen levels, and the soil nitrate and ammonia levels, and the feedback to the upper structure to eventually simulating the N2O flux. And we also using a knowledge guided initialization. Here the chef is ecosystem model is advanced agro-ecosystem model, and at the very complex end of the process-based model, always trying to using the first principles to develop the model. And we use the ecosystem model generate millions of synthetic data to pre-train our AI model, and before using the real world data to fine tune. And what we have found using these two kinds of ways to constrain the model, we have found, first of all, the KGML model accuracy is pretty good comparing to the pure machine learning model, the GRU model, and the process-based model ecosystem. And also, we have surprisingly find that during the period with no data, the machine learning model can have a very strange performance. You can see a peak here. We didn't expect this peak if no fertilization. And while the KGML model presented as a red line perform as stable as the ecosystem model. And during the peak region, and you can find the red line captures those observations better than other models. So we also have compared with the KGML model with other pure machine learning models and have found that the KGML model not only can capture the absolute N2O values and beating all other pure machine learning models, and it can also capture the slope and the curvature of the N2O emissions, meaning it can capture the fast dynamics of the N2O. So that's why I have a conclusion here. KGML better capture the hot moment of the agriculture N2O flux. And then we also extrapolate this model to the whole US Midwest region using the collected 29 sites. And these 29 sites are basically the most comprehensive N2O emission site we can have. And we extrapolate to the regional scale and compare with the atmospheric inversion, which is also something maybe the only thing we can compare in the large scale. And we have found the KGML have the derived results have a better alignment with atmospheric inversion. And this accuracy is one side. And some other interesting thing I would like to see is the KGML model has a better interpretability than the pure machine learning model. Here is a case. And with a pure machine learning model, you might only have the input variables and the output variables. You can also have some post hoc, the explainable AI tools help you to explain how the interfluxes response to different climate drivers and fertilization. But what KGML can do as a additionality, here you can see the KGML can open the black box, tell you that the drivers, precipitation, temperature will not directly influencing the interflux, but they will influencing the soil water content first and soil temperature, and eventually influencing the interflux. So we are adding extra layers in the KGML model, trying to providing the better interpretation of the results. And here, so that with those intermediate variables simulated, the KGML model can have this ability. And we also have the hope that the KGML model can help us refining the process-based model. And the feedback is we can because the KGML model is pre-trained on the process-based model, is first performed as an emulator, and then fine-tuned with real-world data. It can be some processes will be adjusted. We can comparing the model, the KGML model before fine-tune and after fine-tune to find out which processes have significantly changed, so that the processes will need to be improved in the process-based model. And here we find that the processes that in the process-based model, the moisture has a relatively low influence on the NTO emission, while the KGML model, after fine-tuned with the real-world data, it has this part has increased. And we believe that is the reason why KGML model performing better, capturing the NTO hot moment hotspots. So that's we also find that the soil moisture processes in our process-based model need to be further refined. So that is one simple feedback loop. And Greg, I have seen you.
Okay. Yeah, so this is really interesting. So just to understand the dynamics being captured, what does EcoSys do? Is it like a 3D spatial model? Is it kind of a single column model? What does it capture?
The EcoSys model actually is a 1D column model, 1D model. And what it captures is how the fluxes coming out of the land, and can only explained by the environment over the vertical layers of the soil and the plants. Mm-hmm. And what we have given here is extra layers of the soil moisture, temperature. With those two variables, we can better explain why the precipitation and temperature can influence the NTO emissions.
Okay, and do you have to understand farming practices or fertilizer application rates, that kind of stuff?
Yeah, fertilizer rate you can see still being included here. And fertilizer rate is influencing the NTO directly, but there are other factors. Previously, maybe process-based model only treat fertilizer as a single most important factor influencing the NTO flux. But later on, we find that the soil water content might have the similar, or in some cases higher like influencing on the NTO emissions.
Got it. Oh, Jendra.
Yeah.
And Jendra, you had a question?
Yeah, I have one short question. Which process model you use for training the model, and are they also have same sensitivity for moisture, or machine learning model has its unique? Thank you.
Yeah, we are using EcoSys model.
Yeah,
And
I'm assuming you sent the link. I think this is
yeah,
the one you're using, correct?
yes, I
Okay,
mentioned
good.
that one. The ecosystem model. The ecosystem model is mainly based on the first order principles, and then they are trying to develop the such kind of feasible. They do have soil moisture influencing on the N2O, but not strong enough. And these things cannot be fixed by parameter the calibration. We have tested that they cannot be fixed by the calibrating those parameters related to the soil water content, because the ecosystem model didn't have that many adjustable parameters. Most of them can be understood as describing of the environment. And we have, so that we believe the soil model influencing on the N2O has such error in this process-based model is mainly caused by the structure uncertainties. And that's why we use KGML models trying to fix this structure uncertainty. And it turns out it can fix to some extent, but not totally.
Um,
Got it.
Hi,
Thank you.
question.
Yep.
Is this some sort of um, network model?
Oh, okay. So this is a post-processing software called the PCMCI Plus, which is causal inference methods. And why the KGML can do this, because we have intermediate variables being simulated, so that we can have this causal graph being being inferred by those causal inference methods. And the only direct cause, the direct causality being showed in this figure.
Oh, okay, okay.
It's actually interesting. So actually, we had Jacob Runger who did PCMCI in this talk series, and so I'm a fan of the work. So in this case, you're trying to you're treating the traces of the model's output as a data, and then applying causal inference on those traces. Is that right?
I don't totally understand your description, but what we do is yes, we also do this in the cell level observations, and we are doing this in the KGML model and the process-based model. As long as we have a time series of those variables, we can do causal inferences. And the basic idea of this PCMCI, you can refer to the tool. And here we only like illustrated the direct causes, not the indirect causes. And we also have some very strong assumptions, I have to say. So these results are not that reliable, and but can explain to some extent. The not reliable because we have assumptions that variables presented here are independent with each other. So they are, in most of the cases, they are not correct. But that is basically fundamental assumptions you need to run the causal inference.
Right, and this actually is interesting about the state of that community because it's extremely hard. So that's an interesting experience you're having with their tools.
Yeah.
Cool. And then one last thing, at least for me, is when you're training, when you're doing the pre-training, trying to understand the way that knowledge guided is entering the picture. It sounds like you have a generic architecture from software, and you're pre-training it from traces of the simulation, and then independently training it some more from raw measurements. Is that the right, is that your approach?
Yeah, actually it is. We use a pre-training fine-tuning processes in this framework, and the pre-training framework is like mainly use the synthetic data generated from the process-based model. During the fine-tuning, we use preserved learning methods. We reduce the learning rate and checking the responses every maybe a few epochs to ensure the responses didn't deviate too much. If it deviates too much, it means that your model is totally another thing. So that we need to be really careful using real world data to training an emulator. And so that is something we have learned, because we want to compare with a fine-tuned KGML with a process-based model. If we want to do that, we need to maintain the KGML prior knowledge to some extent, at least those responses correct.
Excellent. Oh, and you both?
Hi, question. So you said that this was basically based on one entity or one state influencing another state. So
Yep.
and then how it was trained on, or you got time series data, and then
Yep.
then you trained the ML model based on that, or did causal inference based on that.
Yep.
So two questions. One, what does the time series look like? Does it have like transient behavior? Does it have periodic behavior? Is it going to some steady state? How does it usually look?
Yeah, the thing is, I believe one of the slides previously here is one of the data looks like and time series look like, and
Okay.
we have about 120 days for one piece, and we have several those 120 days and over different years.
Oh, okay. Okay. And another question. Did you explore any other the so-called network reconstruction approaches for this?
Yeah, not yet. So this is like skill has been recently accepted by the EFM, but
Oh, congratulations.
it's a very new paper. So we are still like we may on the stage that trying to exploring different kinds of the graph reconstruction methods. But the PCNCI is one of the methods we have tested before. Is to my extent providing relatively reliable results and within our expectation, but we didn't test the other kind of reconstruction methods yet.
All right, thank you.
Yeah. Thank you very much.
Okay, yeah. Okay, I will keep going and trying to finish my talks, and I'm going through very quick. So when you understand a little bit of what is KGML, how it's implemented, and the next case would be the understanding the carbon budgeting in the agriculture, and the N2O nitric oxide, one of the greenhouses, also can be considered and the carbon budget. And the why we care about the carbon budget, because the market size is huge, like $700 billion globally. And the carbon budget accounts for the input and outputs and changes in carbon stocks within a system. And agriculture plays a dual role in the carbon market, as both as a source like respiration, fertilizer emissions, like I have mentioned before, and also a sink can store it in biomass and soil organic carbon. And understanding such carbon budget is very critical because it can influence in the climate smart farming, carbon credit generation, and supply chain accountability for sustainability claims. And what we want to do is we want to advancing the agriculture carbon budget understanding with the KGML. And this is we use the U.S. Midwest or Corn Belt as a test bed, trying to give a better quantification and explanation of the carbon fluxes, crop yield, and changes in soil carbon stocks with knowledge-guided machine learning. And how did we incorporate the knowledge into this machine learning model? And first, the same, we encode the recipe. This recipe is the understanding of those key variables, how they interact with each other and with the soil pools. We separate the model structure into plant relevant outputs and the soil relevant outputs, and considering the plant feedback to the soil. And we also use the ecosystem model to pre-train the model. And we, in addition to that, we also added a knowledge-guided loss function. So this function is used to maintain the trajectories during the learning. Like beyond the normal objective function, we also added the mass balance function, considering the different variables relationships, threshold controls, because different variables have meanings. Some variables, they have the positive directions so that they can always be sometimes it can always be positive or negative. We need to consider that. And another thing is we also added response control, which is quite important because we want to, during any kind of training, no matter pre-training or fine-tuning, we want to maintain the responses are within our expectation, as I have mentioned before, like preserve those knowledge. And we also use some new data, the data we know that can help this carbon cycle simulations, like gross primary productivity reflecting the photosynthesis to help us help our extrapolation. And what we have find is, first of all, high accuracy. And the red boxes representing the KGML, you can see it overcomes all of those different models. But more like surprisingly, we have find that the KGML model can perform really good in the data zero or data limited situation. You can see it at each subplot left end. And when you're training with very limited data or you don't give any data, it can still perform pretty well. So that is very important in the ecosystems modeling, because in some of the cases, your limitations are very lacking. Another thing is high efficiency. If only running the machine learning model, you may not aware that what the process-based modeler are suffering from previously. If we want to do like high resolution simulation over a large region, like last slide I gave an example, I want to estimate the soil organic carbon changes over 20-year period using a daily resolution and 250-meter resolution. The conventional process-based model will cost 5.9 years using 1,000 CPUs, while the KGML model, when we have finished this construction, it can only need 1.6 days using one GPU. So that is acceleration induced by the hardware improvement and also the machine learning algorithm improvement. And another thing I'd like to highlight is you might also wondering how each component contributed to the KGML performance. Here it is, and we use net ecosystem exchange, a measure of net carbon emission and sequestration as a demonstration. And without any like the data constraints, knowledge constraints, it can have a performance of 0.4, and comparing with the real observations. And when we add assimilating the satellite GPP data, it has a 0.22 performance increasing. And when we add another pre-training into this model, and it has 15% of the performance increase. And while we add structures and the loss functions, eventually we get the knowledge guided the model. And you might wondering that why the structure and loss functions contribute very low to the performance. The reason is the target of the loss function and structure are not aiming to increasing the performance as you have seen our design. What they want to do is trying to add extra layers to the machine learning models, providing better interpretability and not violating some physical or biochemical principles. So those structure and loss function, even though they didn't aiming to improve the performance, they still contribute a little bit here, but significantly contribute to the interpretability. And at the end of this case, I would like to introducing how this model being implemented in the real world are going to be. And we use a carbon credit is some word you may already heard describing the money the insurance company should pay the farmers for their practices and outcomes of the like greenhouse gas reductions. And the basis risk is a term calculating the real outcomes with estimations, and we use absolute values as a basis risk. And we have found when you using the high resolution KGML model can reduce such uncertainties and minimizing the basis risk significantly, and potentially can saving $500 million per year only over the US Corn Belt region. So that will still be a big thing.
So what is a basis risk here?
Okay, basis risk is it's a measure of the estimated carbon credits from some models and the real outcomes from the field. Like we converting the CO2 fluxes into the for example into the dollar value, and we may have an estimation before the year, knowing like how much the greenhouse gases by introducing a practices like no-till can be reduced in the field. And later on, when the farmers when they really like do the practices like no-till practices, and they may observe another real outcomes from the field. And the differences from your estimations and the real outcomes will be the basis risk. And the basis risk, no matter is positive or negative, are harmful to the like carbon program, because nobody want to like it means the losses to farmers or losses to the insurance companies. Okay, yeah.
So in this case, this is emissions from farming.
Yeah.
That you're predicting. So it's avoided emissions is what these carbon offsets would have been.
Yes. Yes.
Got it. Thank you.
Okay. Yeah. Okay. Then we still have one case to go, but I will try to finish like within 5 minutes so that we have a little bit time to discuss more questions. But given we have some success in the agri-ecosystems, I also have a strong interest in the natural ecosystem, especially we like on the wetland and also the methane dynamics. Why I'm carrying that so much, because methane is also a major contributor to the global warming, and it's the second most powerful greenhouse gases right after the CO2, and about 30 times more powerful than the CO2. And the three main like greenhouse gases, you may already know that CO2, CH4, and N2O, we have introduced two, and this is a third. And you can see this figure that the analysis told us that if we want to meet the goal that keep our temperature increasing within 2 Celsius degree by end of the 21st century, only controlling CO2 is not enough. We need to collectively considering reduction of the CH4. But the CH4 dynamics is very complex. It's even more complex than the CO2. Like bridge industry has like to here current decade comparing to the pre-industry has about 3 times increase in the atmosphere, and it also has a very dynamic patterns in the time, so that we cannot explore. Like it has a slowdown increasing period, stable period, and a rapid increase period. If we cannot understand those periods, we cannot understand the how to manage them. So the question would be, what are the sources and sinks of the CH4, and can we explain the CH4 dynamics? Here is a state of art, like one of the state of art findings of the different methane sources. And you can find the wetland contribute about 30%, while anthropogenic microbials like livestock, the rice farming and waste processing contribute about 35%, and the fossil fuel contribute about 30%, and the incomplete combustion contribute about 5%. While the methane sinks, majority being removed from the atmosphere through the chemical reactions, and while the soil contribute about 6%. Today, we are going to focus mainly on the methane sources, wetland contributions, and why we have strong interest in that, because we have a very huge uncertainty here. The uncertainty are mainly caused by the very different, very diverse measurement methods of the methane. And you can see here that the methane observations are ranging from the 1 meter or finer to the very large scale, like over 50 square meter, kilo square meters. And we have if we use this kind of data to constrain different models like top-down inversions, bottom-up modelings, we are going to have quite different results, as you can see here. Then the answer is, can we reduce the discrepancies and can we reduce the uncertainties and by combining all these kind of data? The answer is yes. With the AI modeling, right now we have the capability to do so, but it's still a long way. Here you can see our measurements, like starting from the genomics and to the tall towers, can from the very fine scale to the very coarse scale. And the modeling frameworks right now are also developed in different communities and not communicating that much effectively. And our work is trying to harmonizing all those data, all this model together using the hybrid AI. And this is a work done by the AI for Natural Medicine group, initiated by me and NOAA group. And based on this harmonized data, we have tested different kinds of AI models, transfer learning methods, and out-of-sample scenarios. We have found that with current data settings, most of the AI models can do good at can be good at time out of samples, but they are poor at space out of samples. We have a reason for that. You can check the data distributions global wise for the wetland emissions, and most of them are in the high northern hemisphere, high latitude region. And while we have good performance, the AI performance align with those data distributions, have a good performance in the northern hemisphere, high latitude region, while tropical region and southern hemisphere has a really poor performance. In order to solve these problems, we have different solutions. We have long-term solutions and short-term solutions. Long-term solutions will be we need to build more sites everywhere. And the short-term solutions, we can integrate in scientific knowledge in interpretation. And some examples I would like to demonstrate here is, first, we use a knowledge-guided initialization. We use a process-based model to constrain another different ecosystem process-based model to constrain to pre-train the AI models. We have found it can perform much better than the pure machine learning models trained directly on the real-world data. And you can see the purple line how it well matching with the observations, which presented at dark blue. And another thing is knowledge-guided loss functions, how it can help us. And we have added the causal relationships inferred by the PCMCI plus methods I have introduced before. And here we have observed the significant the performance improve in the model, and also we have the better way to explain the model results. And this is a short-term solutions, but in the long term, we still want some solutions like building more sites. And I would like to emphasize here is AI models can significantly improve the strategic methane monitoring network planning. Here is one work have published last year, and using the simulated results to test the existing networks representativeness and finding the new points which can establish new sites and the best benefit to the global simulations of the methane dynamics. And right after that, this is all the cases I will introduce, and I also would like to introduce the AI for Natural Medicine working group. This working group is currently consists by over 30 scientists global-wise, and we have our annual meeting going to be hosted this October 1 to 3rd, and this is our GitHub, and I would invite you to check our results and our preliminary findings. And our goal is to pushing the frontiers of the global mass and dynamics understanding with AI and provide actionable insights in the greenhouse gas mitigation, and by using the knowledge-guided AI tools. And we also have welcome to different kinds of new peoples as long as they can provide data, resources, or contribute to publications, or they can conduct AI modeling for our working group. So if you are interested, feel free to contact me or the useful links from this GitHub. And at the end, I would like to introducing the knowledge-guided machine learning model, not only limited into the what I have mentioned before. It can also helping in the like water quality, nitrogen concentration predictions, precision agricultures, all those, and those are published papers. And it can also be used to improve the carbon cycle understandings, like by better partitioning the anthropogenic and the hydrotrophic respirations. So that will be all the presentation today. And thank you so much for your patience.
Yeah, thank you very much. One thing that this comes up is because a lot of your approach is based on taking traces from simulations, you actually are not data starved, at least on that portion, the pre-training portion. So you're able to presumably use like heavily parameterized models. So what kind of models have you used as your base ML model, and have you explored transformers and those more flexible family models?
Oh yeah. Oh, you mean machine learning model, right?
Well, which families? Because I'm actually thinking like transformers and like large language models can only work when you have a lot of data.
Yeah.
But you have simulation runs, so you can actually be in that regime.
Yeah. I cannot think that is a really good question. For the previous cases, like 3 cases, CO2, N2O, CH4, they are greenhouse gases simulated by the process-based model I have mentioned. As so, all those process-based model are simulating as a 1D model. And what they care most is the time series of the greenhouse gases. So that's why I'm mainly using the recurrent neural network family. And but in these cases, that's why I call this. I would like to record these different use cases, like for the water quality and the nitrogen concentration simulations. We use graph modeling. We find that the graph will be the most suitable modeling framework for the water quantity and nitrogen concentrations, because the spatial connections between the different watershed and the channels will be the key controlling the model performance. And for the precision agriculture, we believe the convolutional neural network family or transformers might be vision transformers can be a really good fit. And here we use the convolutional neural network and to do to develop to perform as a basic structure of the knowledge-guided machine learning, and we have found it performs pretty well. So in different cases, we might considering based on the task determine the different machine learning model architecture as a basis.
Makes sense. So then another question. One way of consuming these, I'm thinking of these neural climate simulations or geospatial foundation models. And one popular way of consuming them is not to actually run them, but you get the embeddings of this state in space and time is this vector, right? Is that way of consuming some of your models to say have a map across the world of the state of the soil, the forests and whatnot, not as a physically measured quantity, but the embedding of that dynamic?
Yeah, that is a really good question, and we believe the next level embedding based understanding of the ecosystem going to be very cool. And is we are working on several inverse modeling projects trying to reconstruct the embeddings into some physical meanings, because especially in ecosystem modeling, the performance is not always the case we want. The high performance, we might want more interpretability. So the embedding has sometimes embedding is very powerful, but we still want explanation why this embedding helps. Or can they refer to some physical variables? And another question I have noticed you have mentioned about the foundation models and other things. Basically, they are embedding-based structures, and I believe those models are successful because they have a very abundant of data in a group of category. And I believe the group of domains. I believe in the ecosystems, like in some cases, like the water quality, nitrogen concentrations, or the greenhouse gas estimations, especially like N2O-CH4, they may not have sufficient to develop sufficient data to develop such foundation model simulating them. And but I still give a really I'm very happy to see a lot of foundations based on the Earth observations, remote sensings published recently. I believe those embeddings can significantly help. I also noticed that the Google published the Earth benchmark data set recently, and 10 meters, and we are working on that. We are trying to incorporate them to support our framework. But more than directly using the embedding as an input improving our performance, we more want to see why these embeddings helps, and can they refer to some specific plant traits, soil traits, or some structures, some spatial connections over the landscape. So that is a very interesting thing you have mentioned. Thank you.
Okay, that's very fascinating. And then, Jendra, you have a question?
Yeah, I have a question. Can we say that process compared to process-based models, we required less data for in our KGML, and is process model are like point-specific models. We KGML model collect building architecture around same, but extra guided models. So, but the process-based models have a special constraint because of the different properties at different points. Can that problem can be solved by KGML because it is more refined?
Yeah, thank you so much. That is a really good question. So one of the limitations, although I didn't mention previously, is most of those very detailed process-based model are developed as a 1D model, and they can do very some of them have a little spatial connections, but they are poorly presented because maybe most of these models are first developed 20 or 30 years ago, and the computation resources is a big limitation at that point. So most of the model are trying to simplify the model as a 1D, and only put most of the efforts in developing the structure in a very efficient way. And right now we have the power, but we also have some legacy issues because those models are developed 20 years ago with over 1 million lines of code. You cannot immediately turn them into something like spatial connected. And that is exactly what we are trying to do right now. And we have some process-based model have focusing on the spatial connections, like those SWOT plus model, or so those SWOT plus model is like water hydrology model, and trying to consider more of the spatial connections, while the ecosystem model I have mentioned before is a 1D model, more caring about the plant processes and soil processes. And the thing is, previously, these two models are basically developed in two communities, can hardly be combined together. But right now, with AI tools, we might be able to bridge the two models together to considering the 3D connections, 3D interactions between the different pixels. So that will be a really good future directions, but still need some exploration. And another thing is, current KGML model already has a capability to leverage the very fine resolution, large scale, continuous observations like from the remote sensing, so that it can overcome the previous limitations of the pixel simulations to some extent. I hope this answers your question.
Yeah, thank you. Thank you very
Yeah, and
much.
maybe last one, because you're already mentioning it. It sounds like you're thinking of, I'm thinking like Alpha Evolve, where they have a kind of reinforcement learning algorithm, or maybe something like that, and they actively modify the source code of the program based on, the traces of the previous runs. It
Yep.
sounds like you're talking something about the similar. You train a model that says, here's how much better you can be. AI, modify the code of ecosys to do this, and just
Yep.
keep doing this over and over until you have good
Yep.
accuracy with the Fortran, not with the neural net.
Yes. That exactly. The thing is, we still, especially as an ecosystem scientist, I still want to contribute to the scientific understanding improvement. And the goal is not developing one application and then maybe not totally not useful like 2 years later. So the thing is, we want to contribute to something not like in short term but in long term. And the way we contribute is we want to find out the feedback loops from the AI to the science.
Okay, and this also motivates you using like the foundation model, figure out what the signal is, not use them directly.
Yes, exactly.
Okay, it makes a lot of sense. Well, yeah, thank you very much. It was a fascinating talk.
Yeah, thank you.